Okay, so I think we can get started. So one thing I want to make sure is if everyone has select the presentation date, because starting next week, we're gonna do the presentation. I have an announcement. I think I did a quick check. The following student didn't sign up. I think they may have some student already adding their names, but if you haven't done so, please do this as soon as possible. So I think in the first date, we only have Zachary. You're gonna do the first. So if you could, if you haven't signed up, please make sure you also fill out some slot in the first day, right? So as I mentioned, don't be afraid to do this, in the first day. As a matter of fact, it may be good for you, right? So you don't have to bury the burden throughout the rest of the weeks, right? So then you can focus about, completing the code, the report. Otherwise, you still have to, worry about the presentation, all these things. As I mentioned to you guys, if you haven't finished the, project, that's totally fine. I'm not gonna grade this based on the completeness of the project, but purely based on how you present, right, the project, the idea, how you introduce the method, etc. Okay, so make sure you do this before the actual presentation. I won't, accept like the late because we don't have any lectures to make up these presentations. So, and I also emphasize if you enrolled in the in-person and online Zoom version, you have to do this in the live, right? Either come to the class or do this, via Zoom. If you're enrolled in the asynchronized, which is like offline version, I encourage you to do this at least like do the Zoom, via Zoom live version so that you can get a lot of feedback from the student and from me. But if you cannot make it, you have to send me the lecture, the presentation recording, okay? So please do this. If you haven't done so, make the selection, okay? So any questions regarding this? Can you be a little louder? I cannot hear you.
Saying, do you need to submit the presentation slide to web courses before that? Because I saw the deadline is 24 April for the presentation slide submission.
Yeah, so you don't have to submit before your presentation. You can do this after your presentation. So, the presentation will be graded based on how comprehensive, how clear you are able to convey the project idea and the method, right? And also some of the evaluation plans and the progress you have made so far. Just follow the deadline. But you can, if you don't want to do any modifications after you're done with the presentation, you can submit right away. That's totally fine. If you want to make some, modifications, that's okay. You can do this, maybe make some modifications, submit later. But if you want to do any, then you can submit it right away. You don't have to wait till the deadline. Yeah. Okay. And just for the grading purpose, if you're doing like a group project, right, 2 or 3 members, you can submit the same presentation as just do the like proposal, the later report, right? So you can submit the same, just for the grading. Otherwise, if you don't submit, it will show you don't have any submission. On the web course, okay. Okay, see, did I share the right thing? Okay, so before I go to the lecture content, I also want to give you some like general guidelines, right? So common good practice, right? How you can structure your presentation for your project. So this is not like the mandatory, but just my, couple of thoughts or guidelines to help you, right? So if you want to structure, your presentation. So first of all, definitely you want to have a title, authors, right? So if you have doing the individual project, then it's gonna be your name or a couple of names of your team members, okay? And also what is the title of the project, okay? And then you will spend a couple of slides, like 1 or 2 slides, introduce your problem, right? So what is the problem you are working on, right? Why is this problem important, right? So just give some of the background, right, about this problem formulation so we understand we're trying to solve, okay? And also trying, being able to help the audience, right, trying to understand the problem, because some of the, maybe the medical problems you're working on, maybe we didn't discuss, right, during the course, and this is maybe the first time, the audience, has been exposed to this problem, right? So you want to, maybe lay some, build some foundations, right? You can introduce some related work, right? So how is this problem has been done, in the literature, right? So what are the, the main challenges, right, for this problem, and how people trying to propose some solutions to tackle these challenges, right? So you can, provide some of the related work, and also then you can introduce the motivation of the research, right? So, if you want to tackle one particular challenge, right? Let's say there's a couple of limitations of the existing solutions, and you want to address one of them, right? So, and why do you want to address that particular limitation, right? And what is the current prior art maybe fail to do or fail to address that issue, okay? So you want to also provide some of the motivation of the research. And then you can, before you dive deeper into your project, and maybe you can also highlight the contributions, right? So like maybe you're proposing a new approach, right, trying to address this issue, or or maybe you'll come up with a new setting, right, to to address a specific application, right? So that's the contribution side of your project. Okay, so you can make some like an overview, highlight these contributions. And the main part will be the approach, right? So before you explain your approach in details, maybe you can provide a very high level overview, right? So usually if you read a lot of papers, right? So you have been reviewed like 4 or 5 papers so far now. A lot of time, these papers will have like an overview of our approach, right? With the very clear figure, demonstrate, right? What is the input coming to what kind of network architecture or the pipeline, and within this pipeline, what are the modules they've been proposed, right? What's the functionality of each module, right? And what is the output, right? Coming out of these framework. So this is kind of give the audience a very general idea of the approach, right? So they kind of set the stage, okay, what to expect. Maybe later you will explain all these different modules in detail, okay? So when you lay that foundation, then you will introduce the details, right? So as I mentioned, right, you can, based on this outline or this overall framework, you can introduce the component one by one in detail with many slides. And then once everything explained clearly, then you want to do some experimental evaluation, right? So you want to also specify the data set, right? Some of the evaluation settings, the metrics, what are you to use to evaluate, and what are the other methods used for comparison to validate some of the claims, right? So you may say, okay, you address these limitations, then you perform better performance than maybe the prior work, right? So then what are the methods you are used for comparison, right? How do you justify the contributions maybe you mentioned in the, earlier, okay? And you also, if you have enough result, right, you can present the result, quantitative and qualitative, right? So, since we're doing a lot of these kind of dealing with medical images, doing classification, segmentation, all these things, most of them will have quantitative metrics, right? So we talk about, for different tasks, what are the metrics being used, and you can present some quantitative result, numerical result, right? And for better visualization, you can also present some the qualitative result, right? Like segmentation mask, and you can compare with the ground truth and other competing methods, right? Just to showcase, right, how good are your proposed approach. I understand, for some you may not completely complete, the result session. Just present whatever you have, right? So if you have some initial result, that's fine. Just present what you have so far, okay? And to be more complete, right, so you can also provide some ablation study, right, granted that you have conduct a lot of experiment already, then you can maybe do some ablation study, right? So you've reviewed these papers, right? They all have some ablation in their paper. And you can also provide, what is your next step, right? So if you still haven't finished, the project, right, what are the left things to do, right? So you can mention that and how this will be completed. Okay, and finally, maybe just have some takeaway message, right? So what's the conclusion? And just for the good measure, you can mention some future work. So this is not necessarily has to be done within the project, but some general idea you can brainstorm, right? So if I want to further extend, right? So what are the other things I could possibly, work on, right? So that's, this is optional. If you want, you can put this future work. If you don't have any idea, that's totally fine if you don't put this, okay? So yeah, this is like the general guidelines for you to prepare the project presentation. I also shared like two, presentation examples from the previous, courses. I mean, they are not perfect, but just give you some examples, right? How you, present. But you can basically follow my guidelines to prepare if you don't have other, thoughts or ideas. Okay. Any questions? Okay. All right. Great. So then we'll, move to talk about our last topic, which is the federated learning and how it's being applied to, medical image analysis. Okay. So, so far I think we spent most of the time, talk about the conventional or traditional centralized learning paradigm, right? So basically, we gather all the data or the information in the centralized way, right? So either we collect all these data offline, right? So we put that in one place, we formulate a training data, and we train the machine learning model on these data. Then we can, deploy this model for inference, right? So a lot of time, these training has been done, like say, some of the, tech companies, they have some cloud service, right? So the users will, or they collected the data from the user and store in the cloud, right? Gather all the informations to form this training data, and then, we'll train an AI or machine learning model based on these, cloud collected data, and then deploy, this model, right? And maybe the user can query or send this their incoming information, and the model gets some of the result or predictions, and will kind of return this result to the user, right? So a lot of applications, this is done in the centralized training manner. Okay, so there's a couple of good things about this centralized training is because we can collect all these data, right? So usually these models we are trained in a very generalized way, right? So we are able to generalize, into different domains, applications, right? But there's also some potential limitations, right? One is the communication, right? Because the users have to send the data to the cloud, and if you can imagine, right? So if we have this kind of IoT devices, right? So and for some of the regions, right, you don't have like high bandwidth communication, then the communication will become a potential bottleneck, right, for the data transmission and the result returning to the user. And another, limitations you can easily think about is the privacy, right? Because we are sharing the data, right, to the cloud. And a lot of time, these are very private, personalized data, right? Let's say you take some photos, or maybe this is your, like a, smart watch, right? Collecting your vital, activity information, right? So like the movement data, right? The location data, all these things has very sensitive or private information. But if you share this to the cloud, although a lot of these services, they, implement a lot of, encryptions or privacy protection infrastructure, but there's always a risk, right, of this kind of, privacy leakage, maybe have some potential attackers, trying to hijack this information, right? We've heard some uses, right? So there's, there's something like the user data leakage, right? So the privacy is going to be a major concern. And there's also some other, limitations, right? We've talked about this communication, right? And the connectivity is also related to the communication and also the privacy. Another thing is the latency, right? So, usually if the latency also may be, impeded by, the communication as well, right? So if the connectivity is not good, right? If you sending a query, the model return the result or the prediction, then they will create some latencies, right? If the connection is not good. But for some of the applications, right, like the automations, autonomous driving, then the latency is really critical, right? You cannot wait like maybe a couple of seconds. You want the decision to be fed to you instantaneously. Yeah, question, Jeffrey?
I have a question from the perspective of the law, like these gradients are allowed to train, or because let's say that we have a law that do some data privacy. By any chance, do you know if there's a law that they like categorize like these gradients as by valid or not, or right now it's allowed as a component perspective?
The question is it allowed for the user to upload data?
So let's say you have a company, right?
Yeah.
You have, like, let's say Google have iPhones, and then you have personal data on your phones. Let's say the first question is like, can Google train on this personal data?
Right.
And second is like, let's say if there's a law that says you cannot train on this personal data, this gradient, like it's like the law they have look out they have creating laws that take care of this gradient, or if like or these statistics count like this is not the actual data, this can be allowed or something.
Yeah, so there's kind of different layers of protection. So first of all, the personal data, like we are using mobile phones every day, right, on a daily basis. So you may, I think when you download some certain app, right, so you may have experienced, they ask you like consent, right? Do you want to share the data, right? They need your consent. If there's no consent of sharing data, they cannot use, or they won't, automatically on the background to send your data to the cloud. That's illegal, right? Because they don't have your consent. But if you do have the consent to share the data with the company, then there's also a couple of layers for the, potentially remove the personal identifiable information, right? So like for the healthcare, we have the HIPAA regulations that basically, you have to anonymize the patient data, right? So any of this patient sensitive, like the gender, the name, anything related to, or can identify a particular, individual, you have to remove it, okay? And there's also, like in Europe, we have a GDPR, which is another, data privacy protection. I think in the state of California, they have other specific laws to have this kind of privacy. So yeah, so we do have all these laws and regulations, to enforce this kind of data privacy, protection. But again, so I think, doing this kind of data protection, that's kind of like the very first layer, right? You denominize all these informations, but sometimes we can still, infer informations from this kind of anonymized data, right? So we can do cross correlation, right? So especially like in the medical domain, right? We have some genetic data, we have some, medical images like the films, right? Or maybe some other, EHR data. We can do, even though you remove all these, personal information, but you can do this kind of cross correlation, still maybe pinpoint, okay, that these combined data can trace to one particular individual, right? So we still need some certain other, appropriate protection, right? I think the security or protection is going to be a very complex, right? So when we're doing this AI for this kind of, especially for the medicine or healthcare, we have privacy, when data at rest, right? At rest means when you collect data, we have to remove these information. But you also have to do data protection when the data is in transition, right? When you translate data to another hospital or maybe some cloud service, how do you protect that data? And there's also, we can think about how we have to protect the privacy when the data in use, right? In use means you may train the AI model, right? When you're done the transmission, and you have to take that AI data to train the model, right? So that's the data in use, right? So we also have to protect that. We'll talk about some of the things, right? How we can reverse engineering, basically taking the model gradient, how we can reconstruct original data. So that's something we have to protect for the use. So I think this is a very complex topic. There's a lot of active research, but today we'll just basically talk some of the basics and how federated learning can be used as a like extra layer for the protection. Yeah. Okay. Okay. So there's also a shift of the paradigm in the recent years, right? So from the centralized to the decentralized, paradigm, right? So especially here, we have a lot of these, like IoT devices, right? So we have the phones, drones, or maybe some smart cameras, and we also have, different parties, right? Like the hospitals and financial banks institute, right? They have their own data, right? So they want to, each of the party, right, want to learn a model to its own, okay? So this is like, so these data are all kind of distributed across different users, right? And they want to basically customize a model just tailored to their specific data, right? So we want to do this in a decentralized fashion. So if we want to do this, right, so then there's some potential, limitations or risk, right? If we want to train, each of the party want to train a model based on its own data, right? So one potential, maybe the challenge they may face is the local data set may be small, right? So now you are only training a model based on your own data, right? So you are not gathering all the user data in the centralized way and train the model, right? So you only train the model with the local data, right? So, so if you have a very large model, right, so it's over-parameterized, then if your training data is very small, then there's a high risk of model overfitting, right? So we also discussed about, when we, in a couple of the initial classes, right, to train the machine learning model, if the data size is small, then there's a high risk of overfitting, right? And also, there's maybe a risk that the local data set can be biased, right? So just to make some examples, right? So like, like in the healthcare domain, maybe some of the regions or areas, right? So you have medical data that is particular to a certain, race, right? Let's say, in the Florida, we may have a large population of the, Hispanic race, right? So let's look at the maybe breast cancer screening or prediction, for example, right? So if we only look at, the data from the Florida, then the data could be biased, right? So because we may have a lot of, these populations, for the Hispanic population, right? But if you only train the model in this way, then you may not able to generalize well to other race, right? Because there are studies, indicating, different race, maybe you train the model can be biased to their specific distribution. Okay, so in this case, right, we want to also mitigate this issue, right? So if there's the data set, the local data set is biased, right? So if you train this way, the model may not be very generalizable. So the federated learning also trying to kind of address these issues, right? So basically, this federated learning is trying to collaboratively train a machine learning model, right, while keeping the data decentralized. Okay. Yes.
In the case for generalizable models specific to mitigate to, have a model specific for that, one race, so it's really good at detecting, whatever it's, trained for that specific race, and do it, separately? Like, or does it make, more sense to have it more generalizable?
Yeah, so the question is it necessary to always have a generalizable model, but you may want to have some model that is specifically for certain race? Or I think that depends on the application, right? So let's say a certain type of disease that may only occur or has a high frequent occur in a certain population or the race, then collecting a more generalized data may not be very helpful, right? Because you intentionally want the model to be biased to a certain population, right? Because that's maybe the most challenging case, or most the data will be the real world data will be like that, right? So in that case you can say that, okay, that's the nature of this type of application, right? So a biased data is going to be most likely the actual data distribution of the real world data, then that's fine. But if that's not necessarily the case, then you may want to think about, right, do you want to kind of diversify your data to make the model more generalizable, or you are okay with a biased model, right? Because I'm only going to serve in the state of Florida. I'm not going to deploy the model for other state, right? So then maybe that's okay, yeah. Okay, so the further learning is a distributed or decentralized training paradigm. So basically, you are not sharing the data. So all these devices, all the users, right, will not sharing the data to the server. Okay, so all these data will be kept on the user itself. Okay, so just to prevent any data sharing, so that maybe cause some of the data leakage. Okay. So then how does further learning work, right? So because as we mentioned, right, if you only train your local data, then there's some risk of overfitting, and also maybe the model can be biased, right? So then how do we kind of leverage all these data or the knowledge reside in these different users, okay? So, and the idea is very simple, okay? If we don't share the data, then what we can do is we can share the model update, right, or the model parameters, okay? So basically, let's consider a very simple case. You want to do some, medical image classification, right? So you have a classification model, right? Maybe a CNN, network to do the classification. Now, each of the user, let's say this is user data, right? So they are not going to share the data, but each user will have a copy of the CNN model. So all these model will be the same architecture, right? The same initialized weights that will be deployed on these different users. And the user will train this model based on their local data. Okay, so we can say, let me draw this. So we have data, database D1, right? So let's say this is user 1 and this is user 2. So we have D1, D2, and let's say you have n different users. So we have Dn, right? So each of these data can be different. Okay. You can imagine different users maybe collect their own data, right? So not necessarily they share some commonality, okay? So basically these users will train this model based on their local data, and you can train this model for a couple of epochs, right? So then let's say we train this local model, right, 10 epochs. Then what this further learning do is these users will share or sending these model update to the server, okay? So the communication here is not the data anymore, but the model updates, right? So the model parameter, so basically, okay? So the theta 1, that's for the, user 1, right? So that's the neural network parameter, right? So theta 2 is the network parameter for the user 2, okay? So these are different, right? Because they are trained based on their local data, okay? So what the central server receive is a set of these model parameters, okay? So you basically, get a bunch of, model updates, right? So we have theta 1 up till to theta n, right? Because we have n users. Okay. And then how do we, once we receive all these model parameters, right? So how do we aggregate them, right? So how do we collectively learn the knowledge from them? And it turns out it can be very simple, okay? The simple way is we just do the average, okay? So you have n copies of these model updates, right? As we mentioned, they share the same model architecture, right? The same like ResNet 18 or ResNet 50, right? So the same number of parameters and same structures of the parameter. So basically, we can do the aggregation by simply average them, right? So you get like a theta average, right? So let's say theta bar here, which is the average of these n models, okay? So the intuition is that by doing this kind of model averaging or aggregation, the parameters supposedly, or the model is supposed to be stronger, right? Because you learn the representation from these different users, from these different data distributions. Now the server can send these theta bar, which is the aggregated model, right? Supposedly a stronger model, back to the user, right? So each of the user will get an updated model, right? Which is theta bar here. Okay, so everyone will get this theta bar here. And then you can do a next iteration, right? We call this federated learning round, okay? So the second round, what you can do is take this theta bar as the updated model and keep updating it using your local data, okay? So you can, for the user n, right? So in the second federated training round, I'm getting updated global model, theta bar here. Then I'm continue training this using my local data, right, dn here. And I can do this, in a many iteration, right? Once you train this, we can send the model back, and the central server can do the aggregation again, or the average again, then sending the updated model back to the user, and keep doing this, right? So hopefully, by aggregating these model updates, you are collectively, kind of average, use all these complementary information embedded in this model representation, right, to help the user model learning. Okay, so that's a very simple idea of the federated learning. Instead of sharing the data, you are sharing the model parameter to the server. Okay. Okay, so yeah, this one is I'm kind of get a little bit over, ahead of myself. So basically, just what I explained, right? So you do the model aggregation, the server sending the model back to the user, and you can do this again. Okay, so that's the federated learning. Keep the data decentralized, but still able to leverage maybe some complementary information or knowledge from these different users. Okay. So ideally, right, so the final model will be, let's say you do this like multiple, let's say you do this in the K round, right? K round means you have a K, like updated version, right? Ideally, once you finish these federated training, this global model, right? The global model means the one you get from the cloud should have, a similar performance as if you were, collecting all these user data in the centralized way, right? So let's call this FL model, okay? So let's say this is FL theta. So this model parameter is trained in the FL setting. And you also have another way, which is the traditional centralized training, right? So you get all these, the user send all these data to this server, and you train this model, right? Let's call this centralized theta, right? So ideally, you want them to be close to each other, like identical, right? So then you kind of serve the purpose, right? So like you gain the performance like you were doing the centralized training, but you have the benefit of not sharing the data, right? So you have this kind of data privacy protection. Okay, but so that's the ideal case, right? So we want to, the federated learning, the ultimate global model has the similar effect as you would do this in the centralized training. But in reality is, because of these, decentralized or distributed data, right? Users collecting their own data, the distribution will mostly like non-identical, independent, dependent on non-ID distribution, right? And sometimes you're also imbalanced, right? So you just think about maybe I just make this example up. Like you are, let's do the image classification, right? So you have a service that is doing the image classification, but and the company is trying to do this or train this model in the FL way, okay? But different users, their images can be very different, right? Let's say I'm more interested in, travel. So in my photo album, so I have a lot of travel videos or photos, right? But some users, they may interested in certain cuisines, right? So like have a lot of cooking videos, a lot of photos for different food. So you can imagine, right? So these data distributions will be very different, right? So the non-ID nature will make the model, difficult for the model to learn, and it's also very difficult, challenging for further learning to converge to a global minima. So that's the non-ID nature of the data will make the further learning a very difficult process. Okay. So that's kind of the main challenge for the further learning if you want to kind of achieve the level of the performance like the centralized, machine learning. And within the FL learning paradigm, we can also further divide it into, different settings. Okay. So one, we call this cross-device federated learning. Okay. So this is basically, determined by the number of users in this federated learning training paradigm, right? So the cross-device FL means you have a massive number of parties, right? So like can be millions of users. This can be like a phone users, right? So you have an app, so like millions of users using this particular app, right? So then you have all these data distributed on these massive number of users. And within this cross-device setting, right? So they have a small data set per party, right? So you don't have a lot of data, right? Because let's say we don't collect a lot of, or we don't necessarily take a lot of, photos in a period of time, right? And not all the users are always available, right? So you may use the app occasionally, right? You are not always turn on this app, right? Always available. So this app or the users can be on and off frequently, okay? And some parties can be malicious, right? Malicious means they do not contributing very good data, or they may be some malicious attacker, okay? And we also have another setting which is called a cross-silo FL, okay? So in the cross-silo FL, basically we are limiting the number of users or parties into a small amount, not like millions of them, but like 2 to 100, right? Like less than 100 parties, okay? And these parties can be like hospitals or like a financial institute, right? And usually these parties are reliable, right? So they are always, like their service is always on, right? So they are always online. They can participate in the FL training. And they have fairly, large data set, right? So like a medium to large data set, right? Like this financial institute or hospitals, they do have a lot of patients, right? So their data size is appropriate, right? Not have limited data, okay? And usually the parties are typically honest, right? Which means there's not many, they don't have like a bad potential or intention. So they don't have any malicious, users in this cross-silo FL, okay? So in a lot of healthcare settings, we consider this cross-silo FL, right? We have less than 100 parties, and we have a decent number of training data, and these, users are always available during the FL training, right? Not some of the rounds, the user will be disabled or drop out from the FL training. Okay. So with the introduction of this FL concept, right, which is in 2016 by these Google researchers, right, because Google do have a lot of service, and they want to leverage all these user data, but they also want to have this kind of privacy protection. So they come up with this FL training idea, and there's a lot of research in this area. And a lot of open source libraries or framework has been developed to facilitate FL training, right? So we have these like a PySIF, TensorFlow, Federated, Flower, FedML. So all these frameworks are designed, to deploy or train a model in the federated setting, right? So you basically can using these frameworks and trying to, automatically, set up this FL training setting and do the evaluation, okay? So, now you have a basic understanding, right, of what is the FL training, right, how a typical FL training is done. So next we introduce a base algorithm, which is called a Fed average, okay? So, and I kind of describe a little bit, when I, introduce the federated learning paradigm. So for the Fed average, so this is most widely used algorithm, right, for the model aggregation. So basically just taking the average by the name, right, the Fed average. So in the Fed average algorithm, we consider a set of K parties or clients, okay? And each party will hold a data set, right, dk of n k data points, okay? And if we consider the union of all these local data set, right, we have a joint data set D, okay? And, we sum them up, right, so we get the total number of points, okay? So now we want to solve the problem, right? So basically we want to minimize the server, which is we call this global model optimization, right? So we have some loss function, right? So if you are doing the classification, you can using the cross entropy as your loss function, right? So now we are trying to minimize the global model, right, with respect to certain loss function, okay? So for the Fed average, right, so since we are taking the average, now you have like, let's say we have K parties, right? So now we will have, K set of updates, right? So we have FK, which is the model updates from the K's client, right? So theta is the model parameter. And for the Fed average, right, so we basically average all these K models and we get this global model, okay? So this is the optimization for the global model. And nothing different than like the centralized, right? So, and they're very easy to understand, right? Basically we just take the average. One thing you may notice, right, so this is kind of like the weighted average, so I should note, right, so because you have this nk over n, right, so nk is the number of data points for the case user, right. The reason for this is that, let's say I have the user only have 10 data points, right, but I also have some user have like 1 million of data points for their local data, right. As I mentioned earlier, the client data is highly non-ID and it can be imbalanced, right? So you may have a user do not have much data, like 10 data points, but you have like a user have like 1 million of data points. So you cannot treat them equally, right? So obviously the model trained on large data points may be more robust, right? So that's here we are using this kind of weighted average to weight how much contribution each of the model will contribute into the global model, right? The less data points contributing the less, right? Because n is the total number of points, okay? So very simple, just doing the weighted average, doing the aggregation. Okay, so here is the pseudocode, right? So for the Fed average algorithm, so let's look at the, first look at the client side, right? So how the model is doing the training, right? Because the federated learning is you do the local training, send an update to the server do the aggregation, and sending the global model back to the clients, right? So let's see how the local model is doing the training. So basically this you can consider like the centralized training, right? Because within this, local clients, it's a centralized domain, right? So you have, specify the batch size, right? Local training epoch or steps, and also a learning rate, okay? So then this is you doing this gradient descent. So all these typical things, okay? So that's your local model updates. And then let's go back to see what's the, the process with the fed average on the client, on the server side, okay? And for the server side, it will have a client sampling rate, right? So the client sampling rate means, let's say out of K, clients, right? How many clients you want to use? Of course, you can consider all the K clients, right? But you can also do some random sampling, right? Let's say I don't have a lot of, computation resource. The K is very large, like 10 millions of users, right? I cannot, get all these data and do the aggregation. Or the K users, sometimes we call this like a straggler. Straggler means if you want to wait, some straggler means like it has a very slow, the local training, right? Maybe their computing resources are very limited. Like train 10 epochs has to wait like 10 minutes. Other users can down this 10 epoch local training in less than 1 minute, right? Do you want to wait 10 minutes for this one particular user to complete and leverage this model, do the aggregation, or you can ignore that user, right? Because it's just taking too long for the model to update or sending their model update, right? So in this case, you have the flexibility to choose what users to aggregate depending on many factors, right? So the computation on the server or the time constraint, right? I don't wait for everyone to complete. I want to do this very quickly, okay? So you can specify a specific sampling rate, like maybe 80%, 70%, right? So that's a ratio you can define. So in this case, right, so in the server side, right, you have a random set of M clients, right? M clients means a row, which is the sampling rate times the total number of clients, okay? Once you select these M clients, then you can do the, weighted average, right? So get these models and do the weighted average, and that's your server model. Then you can send this server model back to the client, so the clients can do the next round of FL training, okay? Okay, so this is some of the, the result, right? So depends on the number of users and also the communication round, right? So the communication round means how many FL learning round you want to use, right? Obviously, if you train a longer time, right, you have the bandwidth to train multiple rounds, then you will see a higher performance, right? Because you allow the model to train more, so converge better. But sometimes maybe you want to limit these communication round because that involves a lot of resource, right? Each user sending the model to the server sending the model back, right? Back and forth, right? You can reduce the number of back and forth. Obviously, it's going to be better, right? Because you use less resource. So typically in the FL, evaluation settings, we will also taking these kind of communication round as another factor, right? So what kind of algorithm is able to promote a very fast convergence speed, right? Using less federated learning round is able to achieve a certain, threshold of the, accuracy. So then that's also a merit or benefit of that particular algorithm, okay? Okay, so that's the simple federated average, and it's also a widely used because of the simplicity and also a fairly good performance, okay? And another, as we mentioned, right, so the nature of non-ID data distribution in the different clients. So this will cause a problem that is called this model drift, okay? So here, this figure demonstrates what is the model drift means, okay? So here we have, this black, dots, which is the server aggregated or global model, okay? remember, so ultimately, we want a very good server model, right? Just like you are doing in the centralized training, right? That's our goal, okay? We want to have a very good server model, just like you are doing this in the centralized way. Then we can deploy this model for different users, right? For different purpose. But because of the non-ID, right? So each of the clients has their own data. So the optimization may be shift a little bit because the data distribution are different, right? So the client one, I have a different data distribution. Then my local optima maybe go towards this direction, okay? I have another client, right? So I have another different set of data distribution, and my optimization direction may be, the optimal direction may go this way, okay? As you can see that, it's kind of deviate from the central or the global optimization, right? So then in this case, we'll have a difficult time for the model to converge to the global optima. So this is called the client drift issue. So to mitigate this problem, there's some ways to kind of regularize the training. Okay, one solution is you can using some proximal term or basically some regularization term, right, to kind of constrain, right, how limiting the impact of the local updates, right? So let's say for the next round, right, let's say I have a aggregated server sending back to the clients. I don't want the clients deviate too much from this, right? So you can add this proximal term. So this WT is the global server from the previous round, and W here, which is the local updates from a particular client, right? So you can constrain how much of the local deviation from the global, weights, okay? So if it deviate too much, we want to pull it a little bit closer, right? Because otherwise, the model have a difficult time to converge, right? So in this case, we can using this as a constraint to limiting how much of the deviation or updates the local model will perform in the next training. Okay, so that's one way we can do this. Another way is, okay, maybe I don't want you to learn a very good centralized model, right? So why do I need to have a very good centralized model? What I only care about is, can you tailor or customize a model that is only beneficial to my data, right? So in other words, we want to have a personalized model, okay? So in this case, we have the personalized FL learning. So basically, this can also address the non-ID issue, right? Because we have personalized model only tailored to a specific data distribution. So there's also a lot of work that is dedicated, right, to do the personalized federal learning rather than the global federal learning, okay? So I'm not going to dive deeper into this because this is a line of research. If you're interested, you can look into this, basically how you can construct your optimization to fit in their domain-specific data distribution. Okay, so as we kind of discussed, right, so the federal learning do not share the data, but does that mean there's absolutely no privacy concern in this case, right? Because we never share the data to the server, then there's no way for our data to be, kind of leaked or exposed to the public, right? It turns out the answer is no, right? So even though you are not sharing the data to the cloud, but you do share something, right? That something is the model parameter or the model gradient update, okay? And there's some of the research work has shown that we can using these model updates, right, to reverse engineering, trying to reconstruct the data on the local user side, okay? So conceptually, right, so here we have, this is the local client, right, like each GPU is indicating a different user, and this is the user data, right? So here, although we are not sharing the raw data, but we do share like the model updates or gradient to the server, right? So a malicious attacker, right, so you can hijack these model parameter, or maybe a malicious attacker can be a federal learning user, right? Pretend to be like a user participating in the FL training, but the real intention is trying to get the copy of these model updates and trying to recover what other user or client's data, right? So this is a malicious attacker, trying to participate in the FL learning, but the intention is trying to, explore these model updates, trying to recover all these different users' data, right? And let's see how we can achieve this, right? By only knowing these model updates or the parameters, how we can reconstruct the original data. So the idea is very similar as we discussed about the adversarial attack, right? So remember, when we talk about adversarial robustness, right, when we do the adversarial attack, is we trying to add in some of the noise or perturbation to the original image in such a way the model will break, right? Will totally, predicting something very different to the original intent prediction. So in the adversarial attack, right? So the noise we're trying to optimize is the things we're trying to optimize is the added noise, right? So we basically freeze the model parameter, but we adjust the loss function, trying to optimize the noise in such a way the prediction will be either target attack or non-target attack, right? So here, kind of similar idea. So the malicious attacker, right? So have access to these updates, okay? And what it's trying to do is trying to, predicting, right? So let's say I'm trying to figure out what is the data, right? You train this model, we'll give you this kind of model parameter updates, okay? So then I don't have the knowledge about the data, but I can create some of the random initialization, right? I make some random initialization like this, and I trying to adjust these input in such a way when I'm feeding to this model, I get this model parameter exactly as what you shared to the server, right? So the intuition is that if the difference between the updates and the hijacked copy, right? So this normal participant, which is this model updates, if you are able to minimize, if you have certain input that can minimize this discrepancy, then most likely this is the data, maybe used for the training in this participant, right? If you are able to get exactly the same, if you are guessed correctly, right? This is like the cat image, and you feed in this to model, their model update should be very close to each other, right? So in this way, we can using this as the optimization function, right? Reduce the discrepancy between the model parameter or updates to figure out what is the original data, right? So you can reconstruct the original data. So this is called like the gradient inversion, right? So what they call this. So basically you can do this kind of deep leakage from the gradient, right? Or the updates. So you can reconstruct original data. And they've showed that, right? So with this kind of strategy, they are able to, based on the gradient, is able to reconstruct original data, right? So here are some of the how this during the training, and they are able to recover, right, all these trained data, right? So this is the ground truth, and you can see that their reconstructed data is very close, right? So you're able to identify these digits, phase. So in this case, you are able to maybe identify some very important information, right? If you're doing some financial transaction, all these numbers will be reviewed. And if you're doing some patient data, right? So you have some images or some other, surveillance applications, may be able to recover some person identities in this case, okay? So because of these kind of reverse engineering with the model update, right? So we have to basically, federated learning is not like 100% safe, right? So we still have to have other mechanism to prevent the data leakage, okay? So there's some strategies commonly used and also has been used in the industry that is from cryptography, right? So basically doing this homomorphic encryption. So basically this is some encryption technique to encrypt the data. And you can also do this kind of secure multi-party computing, and also you're doing some differential privacy, okay? Differential privacy means you can add in some noise to the gradient update, right? Not the true raw gradient update to the cloud, but you're adding some of the noise to it, right? So in this case, the model gradient can be noisy, and when you do the reverse engineering, you may not necessarily get the original data, okay? But differential privacy is widely used, but the downside is that when you're adding noise to the gradient update, that can also affect the performance of the FL training because you're adding the noise to the gradient, right? Okay, so these are some of the common strategies. So if you're interested, you can maybe read more into this, but we are not going to dive deeper because this is not the if you're doing the cybersecurity kind of research, you may, look into this, right? This homomorphic encryption, secure multi-party computation. Differential privacy is more like in the machine learning domain, but these are more in the cybersecurity kind of research. Okay. So we kind of talk about the general idea of federated learning, right? And also using the Fed average can be a simple method to do this aggregation and to facilitate the training. And we've also kind of mentioned, right, FL learning is not like 100% a guarantee of the data privacy. We can, the malicious attacker can still using the gradient or model parameters to reconstruct the data, right? So all these different aspects for the federated learning. Finally, I want to mention a couple of applications, right? So, what kind of applications that we can use in FL learning, right? So one is we have the IoT devices, right? Like the smartphones, right? We have a lot of applications like the social media, right? So the smartphones, basically have millions of these users, and we can do this cross, device, right? Federated learning. We have a massive amount of these devices, and we can leverage all these data and maybe customize or personalize FL learning to do personalized maybe face detection, voice recognition, hand digit recognition, all these things, okay? And for the organization, right, so this is more related to the cross-silo FL learning, right? So the organization usually has not that many users and also have, trustworthy. And, these can be, hospitals, right, in the healthcare setting and other, maybe organizations, right, like industries, the same industry sectors, right? So manufacturers, they can share the data. They share the knowledge or not necessarily share the data, right? To build some common, industry standards, right? Rather, exchange these sensitive information, but they can share this knowledge with the federated learning to improve their understanding or maybe improve the standards within that particular industry. And yeah, the Internet of Things, right? So we have all these different smart devices, right? So even our, homes has been, incorporated with a lot of smart device, right? The smart thermostat, Alexa, right, from Amazon, and all these, rings, cameras, all these have some sort of AI capability, and we are able to share these knowledges, right, to make the home smarter and especially customized to the particular family or user, right, based on their, habits or preference, okay? And we also talk about, the autonomous vehicle, right? So we can share this knowledge, even on the road, share the bring this situation awareness to this scenario, because we can share this knowledge so that some of the models can be updated in real time. And finally, we can look at some concrete cases, right, for how the federated learning has been, used. So this is the study when we have this COVID-19 outbreak, right? And this study using these federal learning to predict oxygen requirement of patient with COVID-19. So, so the intention is that because I think in the initial stage of the outbreak, because all these hospitals are not prepared for a large volume of patient that has been administered into the hospital, right? So they have limited beds or equipment or resource. How do you distribute these resources to these patients, right? Maybe some of the patient has more severe, COVID-19 symptom, right? So they have a difficulty in breathing, severe cases. Then you maybe want to distribute this kind of oxygen mask or equipment to those patients first, right? Then how do you diagnose this, right? The severity and predict, right, the future, oxygen requirement, so that you can allocate the resource. Because these outbreak, right, is across the different countries, and in the initial stage, maybe we don't have a lot of available data. If you train the model only on the data within this hospital, the model may not be very accurate, right? But the hospitals has very strict regulations about sharing the data, right? Even within the same country, share the data can be a very, cumbersome, practice, right? You have, layers by layers of approval or something like that. By the time it's approved, then maybe it's too late, right? So you want to get these things quickly. And, let alone if you're doing the cross-country data sharing, that's basically impossible, right? So, so to achieve this, right, so this study was carried about the Mass General Birmingham and NVIDIA. So they, using the federal learning technique, right, without sharing the data, but train this model locally for the oxygen, prediction. And they do using different countries of data and trying to make a very good model, right, using FL learning. And this is some of the comparisons, right? If you're only using the local data as the blue bar here, and what's the average accuracy, right? If you're using the federal learning, right, if you're able to aggregate all these knowledges from different countries, different hospitals, and this is the improvement they were able to gain with the green bar. Okay, so using the federal learning, right, aggregating the knowledge from different users do bring substantial improvement into the model performance. Okay. So another use cases is using the federal learning to detect, right, COVID-19 lung abnormality in the CT scan, right? So this is also kind of similar idea, right? So you can using federal learning and to come up with a better model, rather you train on the local data, which may be limited. Okay, don't have a lot of patients. So yeah, so this is how they do this, right? So we have different hospitals and they train their local model and share to the server, and then they do this kind of internal evaluation, right? So either you train the model locally, evaluate on the local data, or you are using the federal learning global model and deploy on the local site to do the evaluation. Okay. So here are some of the healthcare industries. So this is just some very simple cases, some examples, right? So some of the healthcare industry are using the federal learning. So the list goes just way beyond this. So many industries has been using federal learning, because this is a very powerful strategies, and also combined with some other privacy protection technique together, right, to have a very secure private learning strategies, but able to leverage all these knowledges distributed in these different users. Okay. Okay. So yeah, finally have some impact. So I don't have to restate these useful importance, right? So this can be impact to different stakeholders, right? Clinicians, patient, right? Especially patient, right? If you have some personalized model, is able to customize to a particular individual, that would be really good. and also healthcare providers and the manufacturers. Okay. Okay. All right. So there are some other resources have like specific workshop like dedicated federal learning. Especially I've organized this federal vision in the CVPR. So this is the 4th edition. So we also have the 4th edition Fed Vision conference. The workshop in the CVPR 2025. So if you're interested, you can also check our website. Okay, so here are some of the references, surveys, right? Especially the surveys. There's kind of basically summarize all these different techniques and also some of the challenges in FL learning. Okay, all right, so that's all for today. Any questions? Okay, cool. So I have one more lecture. I'm going to cover some other researches in the FL, which will be, I won't spend like a whole class to cover like FL, my research, because there's a lot of technical details. I don't want to dive too deep into that. I probably will also spend like half of lectures just to give you guys, or maybe ask you guys to ask questions, right? We can just basically do like a summary, right? So with all these different lectures or topics we covered for this course, like do you have any specific questions? So, or maybe something we can discuss, right? So let's just have another half of lectures to have this kind of open discussion, right? So something you learn or something you still concerned about, right? You're not very clear. Maybe we can have a discussion there. Then, next 4 lectures will be the project presentation. Okay. Okay. Hopefully you find this class useful. I try to be more diverse on the topics, right? To cover a very comprehensive topics for the medical image processing, also stay on top of the latest trend, right? So I think we covered a very popular, like, diffusion models, multi-model learning, all these self-supervised learning, right? So hopefully, you guys find this interesting. Of course, all these topics I cannot, some of them I just scratch the surface, right? Just give you the high level, but itself can be like a dedicated case or special topic course. We can dive very deeper into this. But the intention of this course is just to give you a very holistic view of these medical image computing and what are the latest techniques, especially in the general vision domain or the AI domain, how we bring this into the medical. A lot of key technologies are just from the general AI domain, right? So, but it's just tailored specifically to the medical data. Right? A lot of these kind of ingredient technique are basically a general technique, okay?
Will these lectures be available even after we are over?
Yeah, you still can have access to the course slides, right? Everything I post online. I think we probably will also post on this on the CRCV YouTube channel. I think that's usually we do. But you can always download that, video lectures save that on the OneDrive or Google Drive. Yeah.
That's what I was going to do.
That's fine. Yeah. Okay. All right. Thank you, everyone. I'll talk to you on Thursday.